So it's important, if we're going to control sound, to understand how sound behaves when it interacts with another body, so some other surface or object. So if we think about the incident sound wave energy, shown in red here, and it's traveling through the air and it hits something, one of three things is going to happen to that incident energy. Part of it may be reflected, okay, and bounce off the object. Part of it might get trapped inside the material or absorbed. It's kind of shown in yellow here. And then part of it may be transmitted or go right through the object, and that's what we'll show in blue. So the green, the yellow, and the blue, those three parts summed up will give us back our incident energy. Okay, no energy is obviously lost in this process, but we're trying to control, through sound control, we're trying to control what happens to that energy. Okay. So the first thing we're going to talk about is absorption, because of these three, we can really only control the amount of absorption or the amount of transmission. And by controlling these two, we're ultimately going to control how much it gets reflected. Okay. So in absorption, I'm trying to trap as much of the sound energy as possible inside the material. Okay, so this will typically be open-celled foams, carpets. If you think about an automotive example, it's the headliner or the carpet. It's got a lot of surface area, a lot of opportunity for that sound wave, those air molecules to come into the material, interact with that material, and then sort of break apart and cause friction. Because ultimately what we're doing with that sound energy in absorption is we're taking that sound energy and converting it to heat through friction. Over on transmission loss side, here we're trying to control the amount of sound that gets through the barrier or through the material. So you can certainly think of a barrier like a door or an apartment building or a hotel, the walls and the ceiling and things like that. If we look first at absorption, we'll talk about the absorption coefficient alpha, and this will give us an idea what percentage of the incident sound energy gets absorbed by the material. Okay, the way it's formulated, it will always be a number between 0 and 1, 0 meaning 0% or none of the incident sound energy is absorbed. Absorption coefficient at 1 means all of the energy that was incident is absorbed in the material, so it's a perfect absorber. In reality, we're going to have some number in between those two extremes. Nothing is perfectly reflective and nothing is going to be perfectly absorptive. If you look at materials that have high absorption, typically we're talking about 80 or 90% absorption, 0.8, 0.9 alphas. Low absorption will be 0.1 or 0.2. And typically alpha will depend not only on thickness, as we'll see in terms of frequencies that are absorbed, but really the porosity, how well air flows through the material. If there's a lot of air resistance or flow resistance for the air, it's going to be a better absorber because it's going to be better at converting sound into heat. Okay, and you see some example absorption coefficients in this table for various materials. So we mentioned the thickness is one of the factors that affects how absorptive a material is. This will recall what we talked about way at the beginning when we were talking about wavelength of sound. The low frequencies have very long wavelengths, right? They're very large in size. High frequencies have a very short wavelength. That physical size property will affect how well a given material or a given material thickness is at absorbing a given frequency. So if you take a foam example here, and I have 30 millimeters of material here, and this is frequency along the x-axis and absorption coefficient in the y-axis, you see it's pretty good at absorbing at these higher frequencies where the wavelengths are small. But it drops off. It gets less and less effective at absorbing as the frequency drops, because at the given thickness there is less and less of that wavelength physical size that's inside that 30 millimeters. So if we double it, you see the absorption coefficient for a given frequency increases quite a bit. So we've drastically improved our low frequency absorption, gotten a sort of a broadband increase all over, but biggest effect is at the low frequency, and then we go all the way up to 100 millimeters and we see drastic improvement in low frequency, modest improvements at high frequency. Okay, and that'll all have to do with the wavelength of sound, and the thickness of the material. So if you need to absorb more at low frequencies, you need to increase the material thickness, or as Pete's about to show us, be smarter with where you put that material thickness.
Yeah, so if you're thinking about like an enclosed area and you're trying to do some absorption, the air molecules kind of set up a standing wave like you see here. And you can see that in the standing wave, there's some places where the air molecules don't move at all. And then there's other places where the air molecules move quite a bit. So the red, you can see some molecules that are highlighted that are really moving, and the blue are some molecules that are not moving at all. And where would you guess is the best place to put this absorptive material, Scott?
Well, I think since we're relying on friction to improve our absorption, I would say these areas of the red molecules where the air is moving a lot.
Yeah, so if we go to the next slide, I think you'll see that if we are judicious about where we put that material, we want to put it really where those molecules are moving a lot, creating friction to get the max absorption effect. And it doesn't really do us a ton of good to put it right against the wall where the air molecules aren't moving. Now, you have to keep in mind this is for one frequency, right? So if you're trying to cover a large frequency range, you're going to have this all over the place because the nodal lines and the active areas change depending on the frequency. But if there was maybe a particular region you wanted to take out, like your Texas region around 1,000 hertz or so, and you knew that was important, you could really be targeted with your material and save some money and cost in your engineering to do some noise abatement.
Very cool.
Quarter wavelength rule, they call it.
So how do we test these quantities? Well, we have some special equipment that we use. This is called an impedance tube. And essentially we're trying to measure the amount of energy, sound energy that's incident. Our material that we're testing is going to be placed inside this tube, and then we're going to try to quantify how much noise or sound energy gets reflected, okay? And we're using this tube to trap all the sound energy inside the tube. No sound energy can get out of the tube, so there's no transmission loss. It's all either incident or reflected or absorbed, okay? So by measuring the incident and the reflected, we're going to be able to calculate how much sound energy is absorbed by our material.
So yeah, we put a small material sample in, like one of those little circles there.
Yep, that's exactly right.
That's what we're actually testing?
Yep.
It's not a hockey puck.
No. Nope.
No, it's a piece of foam that's been cut out.
I look at that and I see an Oreo. So you see hockey puck, I see Oreo.
Well, the one on the right is kind of like a Oreo, but the one on the left, I don't see how you can get to an Oreo.
It's a double stuff, man. Or maybe one of those fudge-covered
Oreos. Is this webinar done soon? You're making me hungry.
I'll meet you at the snack aisle of the grocery store.
Yeah.
Anyway, so these tubes are typically very thick brass or heavy material to trap all that energy inside. Okay, and you see, again, we've got two microphones here. We're going to use those two microphones to be able to tell whether the sound's flowing this way or this way, just like we did with the intensity probe. Okay, and then this guy down here is labeled source. This is where we're actually going to generate the noise or the sound energy. It's just a speaker that broadcasts broadband frequencies down the tube. We see how much goes this way, hits our material, gets absorbed, and then comes back, and that will allow us to calculate absorption. This video will show you some of the highlights of this process. You see there's the sample. It gets placed inside the tube, very specific location. And these materials...
You think an Oreo cookie would have good absorption?
Well, it does absorb milk very well, so I'm going to go with it has a pretty good absorption coefficient.
Yeah, that's a good point, yeah.
But we'll take a lot of care to cut this material sample very precisely so that all of the energy is being captured correctly inside the tube. Test Lab does a great job of helping you figure out your transfer functions. Software leads us through the major steps, does a bunch of averages, and then at the end we get our absorption coefficient. So you see this guy up on the top left is our absorption coefficient versus frequencies.
Yeah, we got close to 1 at some frequencies.
Yeah, so it must be really good at certain frequencies. But this will give us our answer. We could test a bunch of different samples and compare, maybe take an average.
Neat. It was a pleasure presenting with you.
Yes, mine as well.